that it is some discussion. It's of course not finite solution of the problem. First, I want to say a few words about model to which I return at the end of my talk, and in the middle of the talk I will extend the idea of this precision, and some final remarks and maybe some philosophical discussion I leave at the end of my talk. Let us look at the model of the so-called fishing problem or angles problem, but in a specific context. Here I think that anglers catch some fishes according, well, we built a model, stochastic model in continuous time for that, so it is like a special version of renewal process. So let us think that these catches are fishes, and here are weights of these fishes, and there's accounting problems. There are counting processes which describe stream of events. There are two, and here are two, because I assume that in some moments this stream change rapidly and in visual way, and also the events change in visual way. So I need some denotation, like here change for stream and change for weights, and here are the time between the events. So in fact I can build four renewal processes, and if I take into account the resulting point process and resulting catching weights of fishes, I get a following process. So it is this process, and I will think about I will think about this process in a moment of catches of fishes. So in fact this stream of random variables can be described in a following way. So in some moment, which is minimum of these two moments, tau 1, tau 2, the first change or disorder appeared, and second disorder appeared in next moment. So it is sometimes first the intensity of events change, sometimes the weights of fishes change. And the problem which I want to solve is to determine the minimum of tau 1, tau 2 in such a way that this probability will be maximized. The question is what I need to know to construct the reasonable algorithm to determine tau 1 minimum, tau 2. the problem for Poisson, for two independent Poisson processes can be found in paper by Bayraktar and Pur, and for annual processes by Pasternak-Winiarski in his PhD thesis. And when both D1 and D2 is equal D, we calculated this strategy, and in fact not care which knowledge is responsible for accuracy from this side and which is responsible for this side. So now I will think about switching of Markov process, and there is only one moment which change transition probabilities, and after this introduction I skipped this and say only that we have a Bayesian approach, and the model will be constructed here. Here is a history which will be presented during the previous talks, maybe except some application or some special papers like Yoshida, Boydetsky, and I don't remember if the paper concerning application to anomalies in network and epidemiology was mentioned. The problem of switching and solution of this problem for roughly speaking Markov processes was appeared in paper by Yakir and next in Mustakides, and in also in the paper of Yoshida. So we have a priori distribution of disorder moment, and this is with some probability that disorder doesn't appear, and at the first moment we got the observation from the say second group of, so this sequence will be observed, and if disorder appeared, it is with geometric distribution of this moment. So some denotation here is obvious, and let's look at this page. The most important is this formula. What does it mean here? Disorder. In fact, we can think that the second process starts from the state of the last state of first process just one moment before the disorder. And here are the notation which will be used further. It is some likelihood function, and this sequence is a vector of a segment of observation. I will try to show that to have upper accuracy D2, I need a vector of observation last of D2 observation. It will be a main conclusion of my talk. So the distribution of first n random variable of this path we can present in following form, and I define some function which will be useful in calculation. So The problem here is similar, but of course we have only one random variable which describe disorder moment, and using a technique which is well known from, for example, monography of Shiryaev, I changed the problem to some optimal stopping problem. This process will be calculated in the next slide. So, except observation, we will have a posterior process, and the solution of disorder problem will be this tau 0 solution of optimal stopping problem. If we construct this, so it is possible to show that the equivalent optimal stopping problem will be based on some process with d 1 plus 2 coordinates from observation of the process and posterior probability. So it is easy to see that the accuracy D2 it appeared only here, and this accuracy is responsible for this part of payoff function. So from this formula and from the solution of optimal stopping problem will be known that we should keep in mind not only posterior probability, posterior process, but also observation D1 plus 2 observation. Okay. It is a short sketch of proof of this fact. So, of course, some calculation is needed to calculate this probability and this probability, but it gives this formula as I mentioned before. Here is some part of consideration to prove that this multidimensional process is Markovian, and it is seen that this is this important part of sufficient statistics for this problem. For further consideration, for further calculation, this formula is important. So the expected value of such function can be calculated in such way. And standard approximation of dynamic programming give a solution of this optimal stopping problem, and we see that well, we see that this recursive function, which when we take a limit of them, give value of the problem, and well, this is a lemma, and the finite solution is following: that we have a payoff function from left-hand side of this inequality, and here is a threshold which depends on d1 plus 1 observation. And in fact, from this formulation, we see what we need to remember to have accuracy D1. And here is also the form of payoff function, but it is not maybe important. So the most important is the observation from this calculation that this threshold depends on D1, a vector of length D1 plus 1. It is, we go back to this fishing problem, or this renewal process, where we want to determine the minimum of disorder moments, where a disorder can appear in weights of fishes or in intensity, or just time between events. It looks very similar to previous likelihood functions, except that here we have two forms of this likelihood function, because A and B could be 0 or 1. And in further consideration, I will use both forms. In fact, I do some hierarchy denotation, and next I take some kind of expected value with respect of the further disorder, and some denotation which show what happens in fact when first disorder appeared in moment S. So in this using this denotation, I have other form of n-dimensional distribution of this process, and it is something which can be worth to emphasize, that here we have P1, P2, and here are probability of this that disorder not appeared in 0 for first, and here for second. In fact, because the weights and times between events are independent, further I will use so theta equal theta1 minimum theta2 less than n fn is 1 minus pn1, 1 minus pn2. So it is too long to write on the slide. So on the next slide, okay. So here is the problem. I would like to find the same. I want to solve the same problem, or find the disorder moment, minimum of these two disorder moments, and the payoff function here looks. Here is bar, and here should be also bar. So it is this much more complicated function. Here is alpha, but should be 1 minus alpha 1 minus alpha 1 minus alpha 2, according to this denotation. So I don't write in the slides the solution and all calculation, but similarly, like in this one disorder moment for transition probabilities, we have also the same observation that this accuracy depends on determine how many observations we should keep in mind to rationally decide about disorder moment. So the size of this window of observation is here precisely determined. And of course, there is a problem with this that maybe we haven't observation from the first group, and we haven't any disorder. So it should be first decided based on here, based on minimum D1, D2 observation, if in fact we have to wait and try to find the disorder moment or minimum of two disorders. So it is light slide, of course not light because I have some references and some other, but working on this topic, I read also books on philosophy of chance, not only one, but many books, and of course the problem is in any statistical problem, what is the source of chance, of randomness, and if formally correct solution can be applied to some data. The same problem just in the end of the previous talk was mentioned by somebody from audience, and well, taking into account this thinking, I would like to dedicate this my talk to Larry Shepp, who always, when I met him and discuss, he always asked, and where is randomness? Who makes that, or what makes that we are not able to predict, or we don't know what happens in this situation? And the second person who is a good person to be discussed about this is Percy Diaconis, who constructed the machine which shows that throwing a coin is not a random experiment. I think that some of these considerations, which I presented here, especially about fishing, the randomness is obvious, but it is less obvious when angler has a special equipment. So it is maybe model for old style fishermen, not for new style fishermen. So it is a point for the end of my talk. Thank you.
It's quite interesting that, well, Krzysztof, you were the first who mentioned Schuchert paper from 1931 about this quality control charts, right? Because it seems quite interesting that from this style how applications have been changed. So now we're talking about some bioinformatical econometrics applications, and now initially our change point problem was basically about industrial quality control. And from my understanding in the Page's paper, David, am I right, was about say quality control. And now we don't talk about this. Nobody mentioned so far that well there is industry, you must control something, there is a line process or something like this. It's quite.
It is not this paper.
Yeah, exactly. Plus Shiraev's.
Yeah, there are two Shiraevsky.
Yeah, right. From 60s. So it's quite interesting. 30s, I mean 50s, 60s, and now we are just on 21st century. No more industry. Right. So any further questions or comments? Right. So Krzysztof was the last speaker of the last session. So just please have all three speakers of our session.